So up till now, we've been mainly solving equations with just one trig function. Sine theta equals 1/2. Oh, I recognize that from my unit circle. Okay, we've had some multi-revolution questions, we've had some general solutions, and we've seen a couple examples already when you have a trig equation when it has more than one trig function. For example, those ones that were like cos x plus 3 sine squared, blah, blah, blah. And remember, you changed the sine squared to 1 minus cos squared. You were already being introduced to these ideas here where you're using an identity, you're using sine squared plus cos squared equals 1 to help you solve the equation. Now we're going to add a bunch more of those type of questions and look at some strategies of how we can solve them. So we've listed the strategies here, but the best way to see strategies is through some examples, so we'll do that. But number one strategy that you've had so far, and this is what you did when you had that sine squared plus cos squared equals 1, is you try to write an equation with only one trig function. So when you had a sine squared and a cos, well, you changed the sine squared to 1 minus cos squared, so your whole equation was just dealing with cos. That's a strategy you've seen already, and now we're going to add to that not only are you going to try to get it only with one trig function, but with theta only and not 2 theta. So we've introduced our double angle identities. So if you got an equation with a sine 2 theta and a cos, you would change things because you can't solve it if one of them is 2 theta and one of them is theta. So here are the things that you've used. You've used sine squared plus cos squared equals 1 already. We're also going to use our double angle formulas in that situation. Sometimes you can't write it with only one trig function. You might need to factor out a common factor. And sometimes factoring out that common factor separates your trig functions, so you get 2 mini equations that each have only one trig function. And lastly, we sort of use a strategy that we've had in the past. If you get stuck, you can change all things to sine theta and cos theta. Eliminate any fractions because you're solving an equation. So you can multiply both sides by cos or multiply both sides by sine, and then see where you can go from there. So here's our first example. Solve for theta, 0 less than theta less than 2 pi, where cotangent is equal to 2 cos theta. So when looking at this equation, the first thing we notice is we have 2 different trig functions on both sides. So the first thing you would look at, is there a way that I can change everything to just cotangent or everything to just cos? Now the only thing I can think about changing here is I could change cotangent to cos over sine, right? So if I did that, I'd have cos theta over sine theta equals 2 cos theta. Now having done that, that doesn't get rid, or that doesn't change my equation to only have one trig function. In fact, of my strategies so far, I've used the last one a little bit. I changed things to sine and cos. I haven't done that completely because you see we have a fraction now in our equation. And how do you get rid of a fraction? What's the opposite of dividing by sine? You can multiply both sides by sine. So if I do that, if I multiply this side by sine and this side by sine, these ones would simplify, and I'd be left with cos of theta equals 2 cos of theta sine of theta. Now on your take-home assignment, I've seen some of you come to me to check with example number 2 because it sort of comes up similar to this, and have asked, can I divide both sides by cos theta? Okay? So we're not going to do that right now, but this is going to be super tempting for you. Because what would happen if you divide both sides by cos theta? This would go away, and you just have 1 equals 2 sine theta. And now you only have one trig function, and you can solve. Now, that would be nice, but the reason it doesn't work is because if you look at this equation, If cos is equal to 0, what's the left-hand side equal to? It's 0. And if cos is equal to 0 on the right-hand side would equal 0. Is 0 equal to 0? Yes. And so if you divide by cos theta, and since cos theta equals 0 is a solution to this, just by looking, can you see that cos theta equals 0 is a solution? Because that would make 0 equal 0. If you divide by cos theta, without even knowing it, you might be dividing by 0, which apparently is not a good thing, right? This guy tried it. Look what happened to his house. Okay? So what do we do instead of dividing? Because if we divided, for sure it would work. Instead of dividing, we move everything over to one side, make one side equal to 0. So I'll subtract cos theta on both sides, and we use the strategy where we factor. And what factoring does in this case, can you see there's a common factor of cos in both? And if I factor out that common factor of cos, then my two factors that get separated only have one trig function in each factor. So what makes this one equal to 0? Oh, cos theta equals 0, which we already talked about. We knew that that was going to be a solution. What would make this equal to 0? That's when sine theta is equal to a half. So when is cos theta equal to 0? Pi plate. Pi over 2 and 3 pi over 2. When is sine theta equal to a half? Close. Pi over 6 and 5 pi over 6. So now that we're getting close to ending our trig unit, there's going to be times where you're going to run into trig equations later on. What I always want you to do, even though you're going to be allowed to use your unit circle on this test and on subsequent tests, is when you get questions like this, try to do it mentally first. Try to say sine theta equals a half pi over 6. Then use your pi plate to check. But if you're always going to your pi plate first, you're not practicing your memory on those values. No, you do not get to use your unit circle on the exam. So on your exam, they give you a blank unit circle like I did on the last test, and you can fill it out right at the beginning of your test. Okay? So here's our answer. What is the last thing what have we been practicing once we finish a question? Check the domain. So let's check our domain. Oh, 0 to 2 pi. Perfect. Okay? What happens if no domain was mentioned? Then it would be a general solution, which has happened on an exam, I don't know, maybe 7 years ago. They didn't write any domain. And that technically means general solution. But so many people, they're like, oh, no domain, I don't know what to do. And so if no domain is written, it is a general solution. But in this one, we did have a domain. Okay, so here we had to factor and solve. And so we got to see this strategy here and this strategy here in this question. We changed things to sine and cos. At first we did that just to try to get things the same. And we had to factor out a common factor. Here's our next two examples. And prior to them, what's going to happen now is things get complicated because now with the double angle formulas, sometimes they're multi-revolution questions, sometimes they're double angle identities. How do I know when I could use a multi-revolution style to solve it? And how do I know when I should use one of my double angle identities? So if you want to solve something as a multi-revolution question, and you see a 2 theta inside, like this example here, cos 2x minus root 3 over 2 equals 0. Yes? If the only trig function you have is the double angle, then you can solve it as a multi-revolution question. However, on the right-hand side, if you have the double angle and another trig function, so in this example I have sine 2x equals sine x, then you're going to have to use your double angle identity to solve it. So let's look at solving both of these. So the one on the left, we have cos 2x minus root 3 over 2 equals 0. If I get the cos 2x by itself, since I only have that one function with the double angle, I could see this as a multi-revolution question. A review. How do we solve multi-revolution questions? What's the first thing we did? Change our domain. Since 1x is between 0 and 2 pi, that means that 2x's would be between 0 and 4 pi. So for solving for 2x, we would have to go around the circle twice. So when is cos of an angle equal to root 3 over 2? What family? Pi over 6. Quadrant 1 and quadrant 4. See how good you guys are getting at this already? That's the first time around. What will be the two angles the second time around? So you go plus 2 pi, so it'll be 13 pi over 6 and not 17. Right? When you add 2 pi, that's like adding 12 pi over 6, right? So when I add 12 to 1, I get 13. When I add 12 to 11, I'll get 23 pi over 6. And then solving for x, divide each by 2, which is like multiplying by a half. And there are 4 solutions. For our second example, this one we have a double angle plus another trig function. So whenever this is the situation, what you're going to have to do is you're going to have to change your double angle using your formula. Now for sine 2x, there's only one formula for sine 2x. It's 2 sine x cos x. So if I change my sine 2x to 2 sine x cos x, I get this equation. And when we look at this equation and we think of our strategies, we've got sine and cos. Can I change this so that I only have one trig function? Because that's sort of your go-to strategy. And here too you might be tempted, because if sine squared plus cos squared equals 1, you might be tempted to change the cos to 1 minus sine. But it only works if they're squared. Sine squared plus cos squared equals 1. So cos squared is 1 minus sine squared, but cos does not equal 1 minus sine. So the only time you can change sine to cos or cos to sine is if they're squared. If they're not squared, as in this case, there's nothing that you can do. But in this case, then, we're going to go to our factoring strategy. If I bring everything over to one side, so I'll subtract sine x on both sides, I have a common factor in both of those. Again, we don't want to divide by sine, because as you can see, if sine is 0, it makes it work. Instead, whenever you get tempted to divide, you should say, I should factor instead. I have a common factor of sine. If I take that out, well, that splits up my equation and separates my two trig functions. It gets me the answer that sine x equals 0, which I already knew, but it also tells me that cos x could be a half. When is sine x equal to 0? 0, pi, and 2 pi. When is cos x equal to a half? Pi over 3 in quadrant 1 and 5 pi over 3 in quadrant 4. Perfect. And again, we check our domain. We were solving between 0 and 2 pi, and we especially look at our domain. Notice the equal signs with 0 and 2 pi, because we got 0 and 2 pi as an answer. If one of those didn't have an equal sign, we'd have to cancel that one out. Okay. So now we get to the toughest one, example 4. I can go back. In example 4, you see we have a double angle. We have the sine 2x. So the question that we first have to decide is, should we pursue this as a multi-revolution question, or should we pursue this by changing our double angle identity? And because we have sine 2x and a cos squared, we're going to change this. Now that doesn't solve things and make everything in the same trig function. But if I simplify this, what happens when I multiply that half by this function? Does the half go to each thing, or just go to this once? Just once, because it's all multiplication. So the half times the 2, this just becomes sine x cos x. So I have a cos squared, okay, just to go through all of our strategies. I have a cos squared, so I could change that to 1 minus sine squared, but would that help me get everything to the same trig function? No, because I'd still have a cos over here. So changing the cos squared to 1 minus sine squared in this case isn't going to help us any. Do I have a common factor? Yes. So I'm going to just see what happens if I factor that out. So I get cos x, and I'm left with sine x minus cos x inside equal to 0. So what's different in this question is usually when we used our factoring strategy, that separated things and it got one function, cos was by itself. But do you see in this one, we don't have something by itself. Okay? So here, I would get cos x equal to 0. And here, I would get sine x equal to cos x. Oh. Yeah, where is sine x equal? Well, let's do the easy one first. You guys are going right to the hard one right away. That's the fun. I know it's the fun part, but let's leave the fun for the end. Let's start with the boring part. Cos x equals 0. Pi over 2 and 3 pi over 2. All right, now we can get to excited. Where's sine x equal to cos x? Yeah. Pretty sad, eh? When you're getting excited about solving sine x equals cos x. Okay, that's okay. Okay, yes, pi over 4, anywhere else. And why did you pick those two quadrants? Because they're both positive in quadrant 1, and they're both negative in quadrant. Now, the other strategy, when you get sine x equals cos x, the other strategy you can use is there is a way to get this into a single trig function. If you divide both sides by cos, okay, if you divide both sides by cos, you get sine x over cos x equals 1, which is the same as tangent equal to 1. And you get those same answers at pi over 4 and 5 pi over 4. So that works really neat. And for those of you that like to think complicated about math, right? I've been telling you not to divide. I've been telling you to factor instead. Okay? Here I divided by cos to get sine x over cos x. Okay, so the reason I'm allowed to divide from here to here is if I look at just this equation, sine x equals cos x. If cos x equals 0, is it a solution? No, it's not a solution in this case. Even though cos x is equal to 0 over here, which complicates our logical thinking a little bit, within this little equation, cos x equals 0 isn't a solution, so you are allowed to divide in that little equation. But you were able to figure out the pi over 4 and the 5 pi over 4 without that. Okay, so we have about a half an hour left, and the rest of class is a work period for solving trig equations because it's so important. In your textbook, you have the questions 12, 13, 14, and 15. And on that sheet that I gave you, remember that one that says identities with all the happy faces? Okay? On the back side of that sheet was a bunch of solving equations. On the back side of that sheet, I would like you to do 8, 9, 11, 12, 14, 15, 21. Okay? And these numbers that I'm assigning here have nothing to do with the ones that are pre-circled. Okay? So there's when you flip it on the back, there's like, oh, he's already circled the ones you want us to do. No, it's not the case. You don't have to do the circled one. I want you to do these ones. And some of them are calculator and some of them are not calculator.